Passiamo all'English allora. Bon?
Bomb è proprio English.
Ok, aspetta il via. Siamo d'accordo tutti? Sì. So, hi everyone. First of all, let me thank you all for being here today and for coming to this new session of the PRIMO talk. Our speaker today is Greta Malaspina from the University of Novi Sad, and it's a pleasure to introduce to you Greta. Greta got her master's degree at the University of Florence, and she is currently a PhD student at the University of Novi Sad within a challenging PhD plan coupling academia with industry across different countries of the European Union. Today, she'll be talking about a modified Levenberg-Marquardt method for large-scale Newton adjustment. So please, Greta, you can start.
Thank you, Gianmarco. So, as said, I will present an iterative method for large-scale network adjustment problems that is based on classical Levenberg-Marquardt method. And I will just mention that this is a joint work between my university, the University of Novi Sad, and Siux Matwer, which is a consultancy company in Eindhoven. So first, let me introduce the framework that we are considering. So this is our problem. We have a set of points in the plane with unknown coordinates, and then we have a set of observations that are measurements of geometrical quantities involving the points. So, for example, the cases that we consider here are distances between 2 points, the angle formed by 3 points, and point line distances. And then we also assume that we have approximate coordinate observations for the points or for some of the points. And what we want to do is to use the observations to find accurate coordinates of the point. So this is a network adjustment problem. It's also in some sense a localization problem. So there are several different applications in practice, but the ones that we focus on is a project that Siux Matwer is doing for the Dutch cadastre, which has as final goal the vectorization of cadastral maps. So the cadastral archive is made by a set of paper sketches of this kind. So in each sketch represents a portion of land, and for that land you have the division into different properties. So you have crops and buildings and these kind of things. And what they want to do is to put together all these paper sketches and get an accurate cadastral map of the whole country. So this is our problem. Now, since the observations that we have are measurements that someone took in the real world, they are of course not exact. So we cannot hope to find a set of points that satisfies all the observations exactly. So what we do is to look for the set of coordinates that minimizes the error in the least square sense. So we define a least square problem where the unknowns are, of course, our coordinates. And then for each observation, we define a residual function, Rj, where the analytical form of Rj, of course, depends on the kind of observation it corresponds to. So we will define Rj differently depending if the observations is distance or an angle and so on. And then we also divide each residual function by the standard deviation of the corresponding measurement. And this is something that is available to us in the data that we receive from the cadastre. So this is the optimization problem that we want to solve. I said that our method is based on Levenberg-Marquardt method, which is a very standard method for solving least square problems. So I will just briefly recall how it works. It's an iterative method. At each step, at each iteration, we take a step in direction dk, where dk is the solution of this linear system. So here Rk is the vector of residual evaluated at the current point, xk, jk is the Jacobian, and this mu k is a scalar parameter that is updated somehow from iteration to iteration, but we will talk about this later. So what we're interested in here is this linear system, and there are some things that we can say already about this. So first of all, we know that it has 2n times 2, the matrix is 2n times 2n, where n is the number of points that we are trying to localize. And for the problems that we are interested in, we expect this n to be some several millions. So this matrix would be very large, but on the other hand, it's also extremely sparse. Because, for example, we saw that each of the observations that we are considering only involves up to 3 points. So each of these Rj actually involves up to 6 variables, and this is regardless of the size of the problem. And also we could see from the data that each point is involved in a very small number of observations, think between 5 and 10. And this, again, is regardless of the global size of the problem. So this coefficient matrix is indeed very sparse. This is a spy plot of somewhat typical matrix for this kind of problem. So you can see that there are many non-zero elements. And another thing that we can say is that points that are further apart from each other are less likely to be involved in an observation together. And this, again, is more or less intuitive if you think about the cadastre application. Because so our measurements come from these paper sketches, and each of these sketches only represent a very limited area. So even if we put them all together and we consider the whole map of the country, we will still have that, we will still not have an observation involving points that are more than a few hundreds of meters apart. This is because we do not have a paper sketch that is that large. So this reflects, for example, in the coefficient matrix, in the fact that we have these kind of diagonal blocks. And well, just a thing, so this is what the coefficient matrix would look like if we have a nice reordering of the variables and the observations. So if we order the variables so that points that are close in practice are also close when we look at the list of variables, then we can see this almost block diagonal structure of the matrix. Otherwise, we just have to rely on the underlying network, let's say. So what we want to do is to exploit the sparsity and this structure to approximate this linear system with a separable one. So looking again at this matrix, that would mean that we consider just the diagonal blocks. So for example, we would take this block here, and then this large block here, and then this one, and disregard what falls out of these diagonal blocks. Or if we think that this is still too large, we could also take, for example, this that kind of looks like a diagonal block, and then this one, and then this one, and of course we would be disregarding a lot more information. So there is a trade-off here between how good of an approximation we want and how big problems we are willing to consider. So let's be a little bit more formal. So this is the block partitioning that corresponds to what I did before. I'm assuming here that we split into 2 sub-problems. And so this is the coefficient matrix, and this is the corresponding partitioning of the gradient. Now, the most basic thing that we can do if we want to approximate this system with a separable one is to just set to 0 the anti-diagonal blocks. So that would mean that we take as our direction D the solution of these two linear systems, which, as you can see, are independent, so we can solve them separately, even in parallel, and just find this D hat. So the quality of this approximation, so how close D hat is to the exact Levenberg marker direction, depends, of course, on how many non-zero elements we are disregarding. So how many non-zero elements we have in these anti-diagonal blocks. And this is something that is decided when we decide how to split variables. So basically, if we use this approximation here, once we do the splitting, so once we decide how to partition our variables, there is nothing else that we can do in order to improve the quality of the approximation. So what we want to do is to define these separate linear systems in such a way that they're still separable. So we still have the saving in the computation, but we also have some control over the quality of the approximation. And we do that by introducing a correction to the right-hand side. So the left-hand sides are still the same, so the two systems are still separable. And then we take the right-hand sides that we had before, but we also add a correction term that involves this term here, which are the quantities that we disregarded, and then a correction coefficient alpha, which we can compute, for example, in this way. So this is the way that makes more sense from a theoretical point of view, because we are minimizing the residual given by our approximate direction in the exact Levenberg marker system. So once we set this structure, this is the alpha that makes our direction the closest possible to the exact Levenberg marker direction. Now, this is just the basic idea. Of course, here I show just the case where we split in two. We can do this for an arbitrarily large number of sub-problems. We can also consider different forms for these right-hand side corrections. So here we are using the anti-diagonal blocks as they come. We also try to exploit them differently, but this is the choice that seems to work best in practice. And also here I consider the one alpha for both systems. We can also assume that we have independent alphas. In that case, here we will have optimization problem in dimension 2. So this requires some additional computation, but also it would allow us to get a better direction D. So again, we have a trade-off here between the computational cost for actually computing and solving these problems and the quality of the approximation of the direction that we compute. Anyway, this is the scheme of our method. So now I will present some convergence results that we proved and then some numerical results. But before we move to the convergence results for our method, I will just briefly mention the convergence analysis that is done in literature for classical Levenberg marker method. So we can just see what kind of assumptions are used in practice and what kind of convergence results are proved with those assumptions. And this gives us an indication of what kind of results we can also expect for our method. So now we consider just a generic least square problem. This is again the Levenberg marker iteration. Here I also introduced step size that is sometimes used. And again, we have the linear system that defines our direction. We'll first talk about global convergence. Well, these are regularity assumptions. So we have for the function R to be continuously differentiable and for the gradient to be Lipschitz continuous. Well, these are very standard assumptions for least square problems and for unconstrained optimization in general. And then, since here we are interested in global convergence, we need a globalization strategy. And in literature, this is done in mainly two ways. One way is to just take the full step size, so we have dk equal to 1 each iteration, and then we use a trust region scheme to update mu k. And this is the standard choice for Levenberg-Markert. So Levenberg-Markert was originally presented with this update scheme for mu k. What does it mean that we use a trust region scheme? So we can see that if dk is the solution of this linear system, then it's also the minimizer of this function, mkd, where we have two terms. So this term is local model for our objective function around the current point, xk. And then we have this regularization term that somehow controls the norm of D. So if this mu k is large, then the norm of D is pushed to be smaller. If this mu k is small, then the norm of D is allowed to be larger. So in some sense, mu k behaves like the inverse of a trust region radius. And so we updated according to this idea. So that means that we updated according to how much progress we're making in minimizing our objective function. So we consider this ratio here. Here we have the decrease in the given by dk in the objective function. And here we have the decrease given by dk in our model, mk. So if this number is large, then it means that the decrease in the objective function is good compared to the decrease in the model. And so we take a smaller mu k. So we allow D to be larger at the next iteration. While if this is small, then it means that we are not making much progress. So we take a larger mu, and so we force D to be smaller at the next iteration. So this is one way in which we can update mu that ensures global convergence. Another option is to just choose mu k in some other way and then employ a line search strategy. So each iteration, we choose mu k, somehow we compute the direction dk by solving this linear system, and then we use a backtracking strategy to compute the step size dk. So we take ck that satisfies a sufficient decrease condition. So for example, this is standard Armijo condition. And what we have is that if we have these regularity assumptions and then either one of these two globalization strategies, then we can prove that every accumulation point of the sequence generated by Levenberg-Markert method is a stationary point of our objective function. I will just mention that, as I said, this trust region scheme is the standard choice for Levenberg-Markert. The reason why this line search was introduced at some point is that we can see both in practice and in theory that different choices of this mu k can help to make the method faster when we are already close to a solution. So they help improving the convergence rate for local convergence. So this line search can be useful because we can choose mu k in another way to make the method faster at local level, but still retain global convergence because of the line search. So this is more or less the reason or behind this possible choice. Okay, so this is global convergence. Now for local convergence. Well, first of all, we are in local framework, so we consider the set of stationary points, and then we fix one stationary point and we focus on a region around that point. We have again the same regularity assumption. The only difference is that now it's enough to have them on the region that we are considering, of course. And now we have a number of different possible options for the assumptions that we make. First of all, we have to consider the Jacobian. So the standard assumptions would be to assume that the Jacobian is non-singular. But this is somehow a limiting assumption, because one of the reasons to choose Levenberg-Marquardt for least square problems instead of Gauss-Newton is exactly so that we can allow the Jacobian to be non-singular, or to be singular or nearly singular. So this assumption of non-singularity can be annoying sometimes. So in literature, it's often replaced with an error-bound condition, which is an inequality of this kind, which basically controls how the function changes around stationary points. The other thing that we need to decide is if the residual at the solution of our problem is equal to 0. If it is, then we do not need anything else, because in that case we have that taking J transpose J is a good approximation of the Hessian near the solution. Otherwise, we need to add, so if the residual is non-zero, we need to add a condition that in some sense ensures that J transpose J is a good approximation of the Hessian. And this is the assumption that is usually made. And it works because this is in some sense of combined measure of residual and nonlinearity. And so in a neighborhood of stationary points, this tells us how good of an approximation J transpose J is. And then finally, we need to decide how we update the parameter μk. So we can again choose it following the trust region scheme that I showed before, or we can choose it according to the value of the objective function or the value of the gradient. Now here I'm not being very specific, because in different papers there are several ways of choosing these. Some papers they just use this value, and some they use these values as bound, and then they follow a kind of trust region scheme to update μk. So this just means depending on the value of the objective function or of the gradient. So these are the assumptions that are, let's say, common in literature, and these are the results that we can hope to prove. So in the zero residual case, if we follow the standard update for the damping parameters μk, then we need the Jacobian to be non-singular, and this ensures superlinear convergence. If we choose μk depending on the value of the objective function, then we can drop the non-singularity assumption, and it's enough to have that local error bound condition that I showed before. And in this case, we can prove local convergence that goes between superlinear and quadratic, and the rate depends on this S. In the case where the residual of the solution is non-zero, well, first of all, we need this assumption here that we said we use to replace the zero residual assumption. And then we can take the error bound condition. And then the standard choice is to take μk that depends on the gradient. This is because in this case, this number doesn't go to zero. So we could be close to a solution and this RK could still be huge. So the gradient is usually a better choice. And in this case, we still get local convergence, and the rate of convergence depends, in this case, on this delta here. Sometimes these three assumptions are enough. In some cases, depending on the behavior of the Jacobian around the solution, we may need this number S to depend on delta, or we may need some additional assumptions on mu k, which are usually bounds that depend on the constants that appear in the assumption. So, for example, this sigma or the Lipschitz constant, or the constants that appear in these error-bound conditions and quantities of this kind. Okay, so this is the convergence analysis for Levenberg markers. I will now show the two theorems, one global and one local, that we proved for our method. This is the algorithm scheme that we of our method that we use to prove convergence. So first of all, we are not specifying here any way to choose this mu k. We just impose these bounds that depend on the value of the function, and then I suggested a way that was intuitive for choosing that correction coefficient alpha k. But from the theoretical point of view, we need these two bounds to hold. In particular, this first one we need in order to ensure that the direction that we compute is a descent direction. So if we solve the Levenberg marker system directly, exactly, then the direction that we get is a descent direction at the current point. Since we are just solving an approximation, we do not always have that, so we need to enforce it somehow, and this bound ensures that. And then finally, since we are not following the standard update for mu k, we are also using a line search strategy with, again, standard Armijo condition. Okay, so this is the global convergence theorem. We have, again, the same regularity assumptions that I mentioned before, and then we have this additional inequality here, which is just a bound on the norm of the non-zero elements that we disregard when we do the splitting. So this is the only additional assumption that we have with respect to the standard method. And we can prove global convergence in the sense that every accumulation point of the sequence that we generate is a stationary point of the objective function. And then for local convergence, well, we are in the same framework as before, so we fix a stationary point, and we still have the same regularity assumptions. And then, well, we do not want to assume that our Jacobian is non-singular, so we take the error-bound condition instead. And we also know that the residual of the solution is not zero, so we take this approximation inequality as well. So with these assumptions, we can prove that the norm of the direction that we compute is bounded by the distance of xk from the set of stationary points, and this is exactly the same as for standard Levenberg marker method. And then if we also have that this inequality holds, then we can prove linear convergence to a stationary point. And well, this inequality is one of those additional bounds that I was talking about earlier. So we have mu max here, and then we have C1 that comes from here, and then the constants that appear in the assumptions. And so this rho is the maximum relative residual given by the splitting. So this term here is where the fact that we are not solving the linear system exactly plays a role. And yeah, and so this term here is also why we only consider the case where here we have 1. So in the things that I showed before, we could also have better assumption that would correspond to faster convergence. But in this case, since we have this additional term and because of how the proof goes, we were unable to prove anything different than linear convergence, even choosing a larger delta here. So this is what we got until now. Okay, so now I will present a set of numerical results just to understand how the splitting and right-hand side correction influences the performance of the method and the behavior of the method when solving a problem. So in this first slide, we just consider the linear step of the method. So we focus on solving one linear system of this form. For problems of increasing sizes, we solve that linear system with the method without splitting. So k will be the number of subproblems. So k equal to 1 means that we're not splitting. And then k equal to 2, so splitting into 2 subproblems with and without right-hand side correction, where this plus here is kind of expected. So we have that solving the linear system with splitting without right-hand side correction is significantly faster than solving it as a whole. And then we have that the method with right-hand side correction is slower than the method without correction, because we thought that we need some additional computation in order to compute the right-hand side correction. But we can see that it's still cheaper than the method without splitting. Also, just a remark about this, so we saw that once we do the splitting, the linear systems that we get are independent, so we could solve them in parallel, but we are not doing that here. So in all these tests that I'm going to show, we solve them in sequence. So the savings that we have in time is just because solving a linear system has super linear cost. So solving the two linear systems separately is still much cheaper than solving one big linear system. And here we just have a plot for the same set of problems of relative residuals with and without right-hand side correction. So we can see that in practice, the right-hand side correction seems to help to reduce the residual in the linear system, so to increase the quality of the approximation that we get. And okay, so now we consider complete runs of the method. So we consider 3 problems of different sizes, and we consider the methods with k equal to 1, 2, 5, and 10, and the splitted methods are all with right-hand side correction here. And we just plot the residual at each iteration from the initial guess until we arrive at convergence. And so what we can see is that when the problem is small, for example here, the 2 methods with large k requires many more iterations than the methods with k equal to 1 and 2. But then as the size increases, also the methods with larger k require a number of iterations that are closer to the method with k equal to 1 and 2. So here k equal to 5 is really much better than before, and here also k equal to 10. So this happens because if we take a larger k, so we split into a larger number of subproblems, then we are also disregarding more information, because we are disregarding more non-zero elements in the coefficient matrix. And if the problem is small, then the amount of observations that we disregard will be actually large with respect to the total amount. So the approximate direction that we compute will actually be a quite poor approximation of the Levenberg-Markov direction. So the method will need many iterations to find the solution. It still works, but just very slowly. But if the problem is large, then the percentage of observations that we disregard, it's not that large. And so the quality of the approximation that we get is actually better. and so the method will need less iteration to find the solution. And now we have some timings. So again, we consider problems of increasing sizes, and we compare the time necessary to arrive at solution for different values of k. So here, if we look, for example, at k equal to 1, so the blue line, and k equal to 5, we can see that when the problems are small, the method with splitting is actually more expensive than the method without splitting. And this reflects what I said before. So if the problem is small, then the method with splitting requires many more iterations. And even if these iterations are cheaper, it's not enough to balance the larger number of iterations that we need. Then we have an interval of sizes where the method with splitting is cheaper. But then after a certain point, the method with splitting becomes again more expensive than the method without splitting. And here it's kind of the opposite situation happening. So if k is too small with respect to the size of the problem, then the sub-problems are large. And so the right-hand side correction actually requires more additional computation than the computation that we save because we are splitting. So because we are solving separate linear system instead of a large one. Here we have the same test for the comparison between k equal to 1 and k equal to 10. So we can see that for large problems and large in this plot, k equal to 10 seems to reduce the time that we need kind of effectively. We can expect that if we consider problems that are even larger, then something like this will happen. And so the method with k equal to 10 will actually become, again, more expensive than the method without splitting. So that means that we will have to choose a larger k, so to split into a larger number of subproblems. And but this is not an issue because since we are not doing parallelization at the moment, we do not have any, let's say, practical bound on the number of subproblems that we can split into. So we can just choose these k according to the size of the problem. And these are some final timings. So here we try to consider problems that are closer to the ones that we would like to solve. So here we consider problems between 10,000 and 500,000 points, so between 20,000 and 1,000,000 variables. And but we choose the number of subproblems that we split into somehow accordingly to the size of the problem. So this is, for example, the number of subproblems that we split it into for each considered size. And this is just a plot of the timing. So of course, what we are interested in here are not the, let's say, absolute times, because, well, those depend heavily on my implementation and the fact that we are running them on my laptop and so on. So what's really interesting here for us is how the time grows as the size increases. So here we just have a comparison between our timing, which is again the blue line, and what the time would be if it was growing linearly or quadratically or as n to the power of 1.5. So just to have an idea of what we can expect when we solve problems that are of realistic sizes, because here we have 1,000,000 variables, which is still some orders of magnitude smaller than what we would like to solve. And well, this for our purposes is kind of encouraging. From this, it goes as n to the power of 1.2 approximately. We will now try to see what happens if we also introduce some parallelization. So of course, if we split into 120 subproblems, we cannot expect to run 120 things in parallel. But we can, since they're all independent, we can still split them in as much as we are practically allowed, and try to see what happens in that case. This is it. Thank you for your attention. If you have any questions or comments, please.
So thank you very much, Greta, for the very nice talk. And as you said, now it's question time. So if you have questions, you can unmute yourself and ask directly the speaker. So maybe.
Can I make a question? This is Daniela.
Yes, for sure.
Thank you. Just a curiosity. Have you tried to solve the whole system with an iterative method, using maybe a good preconditioner?
We didn't, because we didn't focus on that a lot, I guess. I think we were not able to exploit the sparsity effectively with that. So for the moment, we are solving the linear systems with built-in function, Partitioning, which should be done for sparse systems. But yes, we didn't work much on that.
Okay, but which language are you using to do that?
Python, because the cadastre in the Netherlands requires Python.
Okay. Because now my doubt was this: when you perform your approximation by dividing the matrix in blocks, of course you lose something, you have an error, and you must take it into account. So it would be nice to compare that error with the error that you get when you use an iterative method, I mean a Krylov method, for example, also using a preconditioner. Because in my opinion, you are applying the Levenberg-Marquardt strategy. So when you update mu, your matrices doesn't change much from one iteration to the next one. Actually, only the diagonal changes.
Yes.
So maybe you can use preconditioners that perform updates, or you may also, it depends on mu actually, you may also fix the preconditioner for a few iterations. So it would be nice, interesting, but of course it depends also on the availability of the software that you have.
Yes, but this would be interesting to try, yeah.
Okay. Because also J transpose J is, it is symmetric, positive, semi-definite, okay? But when you add mu, in some sense you regularize, so you actually regularize it. So it is symmetric, positive, definite. So it would be nice to try with the conjugate gradient plus some suitable precondition. I'm saying this because you come from Florence.
Yes.
And I worked on updates for preconditioning with the Stefania and Benedetta.
Yes.
And probably you graduated with one of the two ladies?
Yes, with Stefania.
With Stefania. And we worked together on, actually we had another method, but the strategy was exactly the same. But we worked with the linear, iterative linear solvers. Just a curiosity. Okay, thank you.
No, thank you.
So Greta, once the original splitting of the diagonal blocks is done, you have a correction to recover some of the neglected information on the non-diagonal blocks, right?
Yeah.
But have you considered something like an automatic strategy to choose the original splitting of the diagonal blocks? Because you have a guideline from the numerical tests. Basically, you have a sort of guideline that you can use to choose the splitting, the number of diagonal blocks at the beginning. But do you think that you could try to move to some strategies to do that, or it's just an experimental choice right now?
But you mean to do the splitting or to decide the number of subproblems that we split into?
No, the original splitting. The one that you have at the beginning. So.
Okay, so the splitting. So what in this matrix would be the diagonal blocks, but
yes.
In practice it's not. So the splitting of the variables we do now with Metis, which is an approximation of minimum cut. So basically we take the underlying network. So we define a network where the nodes are our points, and then we place an edge between nodes if they are involved in an observation together. And then we compute an approximation of minimum cut, which means that we look for a set of points that are almost independent. Which, if we reorder everything, this corresponds to this block diagonal structure with not many zeros outside the diagonal blocks. So that is how we do the splitting. For the moment, the number of subproblems that we split into, we just decide looking at the size. But because these last tests, so for significantly large data set, we did like 2 weeks ago. So now we will try to look a little bit more into this to get a sense or a more formal way of choosing this K, so that we do not have to go tentatively.
Okay, thank you. Thank you so much.
Thank you.
So
Marco raised
other questions?
Hands?
Yes, yeah, maybe it's a stupid one, but you know, it's just out of curiosity.
Yeah.
Would it be possible to devise an adaptive strategy for the splitting of the problem, in the sense that instead of fixing it at the beginning, try to, for example, at the beginning, I imagine that since you showed us, and it's reasonable that when you split the problem too much, it takes too many iterations because your system become too inexact, let's say. But could be possible, for example, to start with some small number of splitting in order to move to a better region and then increase the number of splitting in order to reach the solution, or in general to find an adaptive strategy so that by looking at the residual of the system, decide whether or not to change the number of splits. Would it be too expensive? This also
no. We are thinking about this. If it's worth either computing a different splitting or computing a different splitting, also splitting into a different number of subproblems. That is very cheap compared to the global computation. So we cannot do it at each iteration, but we can do it a few times along the run of the method. We are thinking about this. We didn't try yet. So one option could be, for example, to split into a large number of subproblems at the beginning, where even if we are kind of inaccurate, it's still okay. And then split into smaller, into a smaller number of subproblems when you are close to a solution and you need some some better approximation. So you would, for example, here maybe switch to a smaller number K, so that you don't have this long tail here, and maybe they will converge faster. That's an option.
Okay. And because I think that you could be able to find some way of controlling it by what you leave out, and so comparison on the residual, something like.
Yeah.
But yeah, I think I thought it the other way around, and maybe you're right. It's better if you start with a large number and then you restrict at the very end in order to go fast to the solution instead of wasting.
Well, I don't know. This is what I thought now.
Yeah, no, but by looking at the plots,
but, yeah.
by looking at the plots, if you see the first one, you see that the residual tries to, so the decrease changes, and at some point the decrease is becomes very slow. So maybe at that point, you're right, you could just decide to reduce the number of sub-problems, go straight to the solution, and maybe save a lot of time.
Yeah.
But okay, thank you.
Thank you.
Are there any other questions from the audience? Let me check in the chat. No. So it seems to me that there are no further questions. So maybe we can conclude. And thanks again for joining us, and see you in 2 weeks for the next PRIMO talk. And we thank Greta once again. Thank you.
Thank you.